Let's start a new chapter as we continue our study of rings. So this is going to be chapter 19. It's called Integral Domain. So an integral domain is an important type of ring, and we're gonna learn what that is soon. But let's sort of introduce the topic like this. So here's a key property. So a key property of, well, it's a key property of a lot of different places, but let's just look at the real number. So a key property of R goes like this. Let's say that you have a couple of real numbers. So if A and B are in R, and when you multiply them, you get 0, then you automatically get to conclude that one or more of those numbers right there is 0, right? So then A equals 0 or B equals 0. That's a typical thing. I mean, we sort of do that in our sleep, right? We're used to this property when we're working with numbers. And we use this. Here's one of the main reasons that this is important, or at least here is an important reason. How do I want to say that? This property is important for a number of different reasons. Here is one. So for example, let's say that we have right, x squared minus 4, the polynomial, equal to 0, right? This is true if and only if x minus 2, x plus 2 equals 0, if and only if x minus 2, so notice here, if we're working with real numbers, this is true if and only if either this factor is equal to 0 or that factor is equal to 0, right? Just using this property right here. And so that means that x minus 2 equals 0 or x plus 2 equals 0. All right, that's using this key property. And then this would be if and only if x is equal to plus or minus 2. So we use this property when factoring polynomials, right? So, so we use this property when we find roots of polynomials by factoring. So we use this property when finding roots of polynomials by factoring. Right, so this is a crucial property of the real numbers. But this property does not hold in all rings. So this property does not hold for all rings. And so here's a sort of easy example. In Z6, note that if you multiply 2 times 3, right, that's equal to 0. So we have a couple of non-zero elements of Z6 multiplied together to give us 0. Okay, so this leads to a definition. So let's let, so let's take a ring R. So let's let R be a ring, and let's say little r and little s be non-zero elements of R. Remember, R star means everything except for the additive identity. Remember, when I say non-zero, I just mean not equal to the identity. It's not necessarily the number 0. Okay, so we have a couple of non-zero elements of our ring. Now, if I need to finish off this definition. So if let's do it up here, I guess, Rs. So if Rs is equal to 0, then R and S, they're called zero divisors. So R and S are 0 divisors, right? So zero divisors are non-zero numbers so that when you multiply them together, you get 0. So let's look at another example here. So let's let A in Z sub n star, where the GCD of A and n is equal to 1. So I want A and n to be relatively prime. And suppose that A times B is equal to 0 for some little b in Z n star. Oh, you know what? Let's drop the star there. So let's just say, suppose that this happens for some element. What I'm going to do is I want to show that B actually has to be 0. So, what does that mean? Okay, so if A times B is equal to 0, what that means is that n divides A times B. So it follows that n divides A times B. But A and n are relatively prime. So if n divides this product, and n and A are relatively prime, then we know that n has to divide B. Right? So since A and n are relatively prime, then what's that called? I want to say it's called Euclid's lemma, but I think it's Euclid's lemma. Why is the name escaping me right now? I want to say Euclid's lemma. But anyways, it's a fact. If since A and n are relatively prime, we conclude that n divides B. So what does that tell us if n divides B? That means that B is 0. So that is B equals 0 in Zn. So what's our conclusion? Our conclusion is that if A is relatively prime to n, then A is not a 0 divisor. So conclusion, if A is relatively prime to n, then A is not a 0 divisor in Zn. On the other hand, if the GCD of A and n, let's say, is equal to D strictly greater than 1, then when I look at, what am I going to do? A times n over D, that's equal to A over D times n. And so what do we have? This is going to be an integer times n, right? We know that that's equal to 0 in Zn. And so what does that tell us? If you are not relatively prime to n, then you are a 0 divisor. So we can say, therefore, A is a 0 divisor. Right, so this completely characterizes the 0 divisors within Zn. In fact, yeah, let's write this down. I'm not going to call it a theorem, right? It's more just like a fact. So we have shown that in Zn, A is a zero divisor. I guess I need to show A. I gotta say non-zero. So A in Zn star is a zero divisor if and only if GCD of A and N is strictly greater than 1. One quick consequence, what if n was prime, right? So, let's say p. So as a consequence, if p is prime, then ZP has no zero divisors. Sorry, you have to sit here watching me try to open this box of chalk here. Let's see, what else? Oh, yeah. Okay, so here's another property that we use. So another key property of R is the cancellation property. So is cancellation. And so it goes like this. Oh, and it turns out this property, or these two properties, are actually equivalent to that first property that we're talking about, the non-zero divisor property. So it goes like this. So cancellation, I guess I should say R of the cancellation laws. Let's say another key property of R is cancel. Yeah, let's just word it like this. So if AB equals AC, yeah, and A is not equal to 0, then B equals C. So this is left cancellation. And then we can say it in the reverse order also. So if BA equals CA and A not equal to 0, then B equals C, so that's right cancellation. Right, you use that when you're doing algebra, right? You use that property all the time. Right, I mean, it's basically what allows us to solve equations. Right, but this does not hold in general also. So these, I don't know if I want to say this or these do not hold in all rings. And so let's give a quick example. In Z12, what we have is 2 times 4 equals 8, which is equal to 2 times 10. Oh, 2 times 10. All right, but I can't cancel the 2's and conclude that 4 is equal to 10 because 4 and 10 are not the same in Z12. All right, so but 4 not equal to 10 in Z12. So cancellation property does not hold in general either. So now what I'm going to show is that having the first property that we talked about, right, the no zero divisors property, is equivalent to having the cancellation property, or properties. So let's say it like this. So this will be our first theorem of the chapter. The left and right cancellation properties hold in the ring R if and only if R has no zero divisors. So for the proof in the forward direction, if we assume that left and right cancellation holds, so let's assume cancellation holds, yeah, let's choose a non-zero. So, and let's say let little a be an R star. Now, if we have AB equal to 0, oh, but wait a minute, A times B is equal to, sorry, AB equal to 0, but 0 is equal to A times 0. A is non-zero. Since the cancellation properties hold, we have to conclude that B equals the thing on the right-hand side over here. Then we have B equals 0. So that tells us that A could not be a zero divisor. So no matter what non-zero element I choose, if it multiplies times some other element, it gives us 0. That other element has to be 0, right? So there's no zero divisors. Okay, so now in the reverse direction, we're going to assume that we have no zero divisors. So assume R has no zero divisors. So now I need to show that the cancellation rules hold. So suppose that A, what do I want to do? AB, yeah. Suppose AB is equal to AC, where A is not equal to 0. Okay, so then AB minus AC is equal to 0. And if I factor the A out, A times B minus C has to equal 0. Now, since we have no zero divisors and we know that A is non-zero, that forces us to conclude that B minus C equals equal to 0. So it follows that B minus C equals 0. And so B equals C. So that proves the left cancellation, and then the proof of the right cancellation would be basically the same. So similarly, right cancellation holds in capital R. Okay, so that proof is not too difficult. More or less just kind of a follow your nose type proof. And now we're ready for the definition that gave our chapter its name. So a commutative ring with one, we want to have at least two elements, so a non-trivial commutative ring with one is, oh yeah, let's say this a little better. So a commutative ring with unity and no zero divisors is called an integral domain. So here's a few examples. Z is an integral domain. Right? If you take two non-zero integers and multiply them together, you're not getting zero. Zn is an integral domain, which I usually abbreviate capital ID, if and only if n is prime. That follows from the computations we did earlier. If R and S are integral domains, then if you look at the direct product, R cross S, definitely not an integral domain. Right, so this is not an integral domain. Now, how do we prove that, or how do I, why is that true? So the reason, so let's see, what I want to do is I want to cook up a couple of non-zero elements so that when I multiply them, I get zero. So let's take R, little r in R star, and S in S star. And we've assumed, right, that there is at least one non-zero element in each of these two rings right here. So then, look what happens if I multiply R comma 0 times 0 comma S. That's going to give us 0, 0, right? And so here are two non-zero elements. When we multiply, we get 0. Let's do one more result, and then we'll call it a day. So theorem 19.2, if F is a field, then F is an integral domain. So fields are always integral domains. So F is an integral domain. The proof. So by definition, F is a commutative ring with one, right, with unity not equal to 0, right? So every field has at least two elements. So now let's choose a non-zero element. So let's let little a be in F star, and suppose that AB is equal to 0 for some little b in capital F. Okay, so what do I want to do? I want to show that A cannot be a zero divisor, which means that I need to show that B is equal to 0. Well, remember, we're in a field, which means that every non-zero element has an inverse, a multiplicative inverse. Right? So then, if I multiply both sides of this equation by A inverse, look what we get. We get B equals A inverse times AB, which is equal to A inverse times 0, which is equal to 0, so B is equal to 0. Right, so therefore, F has no zero divisors. Okay, that's a good place to stop for today, so we'll see you next time.